In this video, we'll be going over the answers for Thursday, April 9th. And what we're talking about today is the electromagnetic spectrum and light in general. So light can behave both as a particle and as a wave. Here, we're just kind of looking at light as a wave. So when you have a wave, you have two different things you can measure that wave in terms of. You can do it in terms of frequency, that is how fast the wave's moving, and wavelength, how big is the wave. And these two are inversely proportional. That is, the faster your wave moves, the smaller the wave. Also, we can throw energy into the equation. So high energy waves are very fast. They repeat very frequently, and they have a very short wavelength. They're very short. If you think of a wave has a top and a bottom, and this wavelength is just the distance between the tops of the wave. While if you have a very long wavelength, you're very slow and you're low energy. There's a very small portion of light that we can see that we call visible light, and that's where we get all our colors from. So our first question is just looking at understanding light. So list these radiations in terms of first increasing wavelength. So the smallest wavelength, your highest energy, is UV radiation, then infrared, then micro, then radio. Then the energy of the waves. Well, that's going to be the opposite trend. So your radio waves had the longest wavelength, so they're also the lowest energy. So if we rank them from low to big energy, it's A, B, C, D. Now, we were talking about velocity and wavelength on the last slide, and the way we connect those two properties is with the speed of light. The velocity of the wavelength of light equals the speed of light divided by its wavelength. So, the frequency, that's what this phi is. Frequency equals speed of light divided by wavelength. And the speed of light is a constant. And so with these, we can go between frequency and wavelength no problem. So first we have 100.2 megahertz radiation. What's the wavelength? So whenever we're using these equations, we have to be in either hertz, which are 1 divided by second, or we have to be in meters. Right now we're in megahertz. So the first thing I did was convert megahertz to hertz. So you go back to the table that we've been using all semester, and you see, well, 1 mega is 1 times 10 to the 6 regular. So megahertz, 100.2 megahertz, is 100.2 times 10 to the 6 hertz, or 1 divided by second. Then I want to find out wavelength. So what I did is I just switched these two in the equation. And so the way to actually do that, if you imagine wavelength was still on the bottom, multiply each side by wavelength, then divide each side by frequency. That's how you can flop these two. So I have the speed of light divided by our frequency, and you'll see that this has a wavelength of 2.99 or 3 meters. C is doing the opposite. I start with a wavelength. What's the frequency? So again, I'm going to convert to meters. I start in nanometers using my table. I see 1 nanometer is 1.0 times 10 to the 9th meters. So this is 632.8 times 10 to the 9 meters. I can calculate my frequency from this, just using the equation as is. Frequency equals speed of light divided by my wavelength, and I get 4.74 times 10 to the 14th. Question 3, this is complex, so let's work through it. I have a heat lamp that produces 32.8 watts of power with a wavelength of 6.5 micrometers. How many photons are emitted per second? And a watt is 1 joule per second. Alright, so here's my heat lamp. It's throwing off heat, 32.8 joules per second worth of heat, and my wavelength is 6.5 micrometers. The first thing I wanted to find out is what is the energy of one photon? And here we have to use a slightly different equation. The energy of one photon, E, equals Planck's constant, h, which is just a constant, multiplied by the speed of light, divided by the wavelength of that light. So I'm in micrometers. I want to be in meters. So that's 6.5 times 10 to the 6 meters. That's my wavelength. That's my denominator. Speed of light's a constant. And Planck's constant is a constant. So I put these in, solve for E. And what I find from that is that the energy of one photon is 3.06 times 10 to the minus 20 joules. So that's how you write it out. E equals 3.06 times 10 to the minus 20 joules per photon. Now, how many photons are emitted per second? That's what I'm trying to calculate. Photons divided by second. That should be my N unit. Well, my lamp is 32.8 joules per second. And I have 3.06 times 10 to the minus 20 joules per photon. Joules are canceled out. My units are photon per second, which probably means I did this right. So this lamp, the number of photons are 1.07 times 10 to the 21 photons per second. With that, that ends this video. If you have any questions, please don't hesitate to contact me. Otherwise, I'll see you in the next video.